today's topic, combination of improper integral. L is missing here, right? Improper integral, but that requires trig sub to integrate. Oh boy. Okay, so fasten your seatbelt and here we go. In order to do this, first thing we do is we have to figure out how to find the antiderivative, right? So I'm gonna do that part here, okay? So let's do the antiderivative part. That's thick. I'm gonna zoom out a little bit. So the antiderivative part, which is dx and over square root of x squared minus a squared, right? That part. What should we say x is? What is the trig sub trig?
A secant theta.
A secant theta is correct. And the reason for that is number one, dx then becomes a secant theta, tangent theta, d theta. But more importantly, this part, right? You plug in a, so it becomes a squared secant squared. So do you agree that this thing, I'll just write it. So we have a squared, common factors, secant squared theta minus 1, right? And then that thingy, of course, is tangent theta. So far, so good? Okay, now, do we need an absolute value here? Whenever you take a square root of something square, you always think about absolute value. A is positive. Usually you do, because secant is defined in first and second quadrant. Okay, and in second quadrant, tangent theta is negative, so you do absolutely have to put absolute, this thingy. But let's look at our definite integral, okay? I purposely wanted to avoid this second quadrant, otherwise this integral is not even defined. You know what I'm saying? We cannot have this x squared less than a squared. So x is greater than a and a is positive. How's that? So we are looking at first quadrant only. That's the only reason I don't have absolute value here, but normally you do, okay? Now, then this thingy becomes, okay, dx over that thingy, so this thingy over this thingy. You see a's cancel, tangent theta cancel, so you just have secant theta, right? So far, so good. Now let's review this. All of these reviews, these are great reviews. What was the trick in evaluating this? Multiplying the numerator and denominator by this thingy. Okay. Now if we do, the numerator becomes secant squared theta plus secant theta, tangent theta, and d theta. And then do you see this is a u sub now, right? Do you see this is u and that's your du? Could we do that much in our head, or you want me to write u and do it for you? I just write this thing as a reference, then it's a u sub. U is equal to secant theta plus tangent theta. And then du will become, this is a nice trick, just to write it down here. So we have secant theta, tangent theta, derivative of secant, plus, and then derivative of tangent is this. And now you just think about it, 1 over u, and then we actually don't substitute it. So this becomes 1 over u. You know what I'm saying? And then it's just like, yeah, u. So it's like ln, and then secant theta plus tangent theta. You get it? So first you just write this and then, okay, that's ln u. So you just never really substitute. And once you get good at it, you just imagine this part. Then you can do this u sub in our head. So far, so good. Now, then, what is secant theta? Well, we can find it from here, right? Secant theta, of course, is x over a. Good. Plus, what is tangent theta then? Right? Do we have to draw the triangle? No, you don't. Look, here's the tangent theta. That's the square root thingy over A now, isn't it? If you draw it, it turns out to be that. You want me to draw it for you while we're at it? Okay, let's draw it. I'm gonna draw it. I mean, it's a good exercise, so let's draw it right here. And if you have triangle, like this, so we are calling this thingy A, well, secant theta is x over A, isn't it? Now, in this case, we can actually put x in the numerator, I mean the hypotenuse, because I usually said, no, don't put any variable bit there, but x is positive in this case, so it's fine, we can put it, right? This is the easier way. And then this side right here is x squared minus a squared, isn't it? So when we have tangent is this over this. Wow, but then we could have easily got that from here. So we have square root of x squared minus a squared over a plus c is the antiderivative part. Good. Now we will do an integral part. Okay, I'm gonna change the color and go down. So my integral from, what was it, 0a to infinity of dx over square root of x squared minus a squared. Now we have to write it like this. However, do you notice that there are two different improper sides? See, once you plug in a here, that denominator, there's a vertical asymptote. Denominator becomes 0. And then, of course, there's an infinity side. So we have A approaching. We already used A, right? So B approaching A from the right-hand side. And then we have to replace that with B because we cannot substitute A. And to where do you want to break it up? Don't have a good number. C. Any arbitrary number C. And then we have, now we can, we still write it, so square root of x squared minus a squared, then plus the limit, and this one will be c to d. You know what I'm saying? And then d will approach infinity. And dx over square root of x squared minus a squared. Are you with me? So C is some arbitrary middle point. So let me write that down here. So my B is greater than A. And then, of course, there's a C, and then there's a D in that order. You get it? So C is just some arbitrary point that is between B and a D. Okay. Now we recycle our work from up there. So we have limit of B approaching A from the left-hand side, and it is ln. And then we have x over A plus square root of x squared minus a squared over A D, and close from B to C, plus another limit of, this time, d approaching infinity, and then ln of the same thing. And this limit approaches from C to D. You with me so far? Okay, let's take a limit. So B will approach A, right? Okay, so this thing becomes 1 then, right? And this thingy becomes 0. So we have ln 1, right? Oh, we have to substitute before we have. I jumped the gun. Limit b approaching a. This is pain in the butt, isn't it? I mean, especially if you have two limits going on and the same problem. So we have ln of b c over a plus square root of c squared minus a squared over a squared thingy, and minus ln of now b over a plus square root of b squared minus a squared over a squared. That's just half of it, and the other half, holy cow, right? Yeah. The other half is, oh, not equal to, plus limit of d approaching infinity of ln, and then we have d over c, I mean a, that looks ugly, a plus square root of the now d squared minus a squared over a close, and then minus ln, and then finally c over a plus square root of c squared minus a squared over a close, and close the bracket. Whew. Now, let's compare this thingy with this thingy. There's no b here. The limit is approaching b, and the limit is d is approaching. There's no d here. So these two are just unaffected by the limit. Then do you see those two cancel?
Mr. Kim.
Yeah.
I just have a question. Why is the denominator a square on the first ln term?
Did I write a square? Oh my god. That's because I screwed up. Huh. How's that? Good? Nice catch. So these two at least cancel, so we don't have to write these two no more. Now we'll take the limit, okay? So when we take the limit, b becomes a, so this becomes 1, right? This thingy becomes 1, and this thingy, b becomes a, so this thingy becomes 0. So far so good, so we have ln 1. Say yes. Okay, and d approaches infinity. That means this whole thing approaches infinity now, doesn't it? Say yes. Right, ln of infinity is still infinity. So what we have left after all that is to find out this is infinity. So this thing diverges on me. Holy cow, right? I mean, isn't this one of the most complex things you have ever done, or what? And then you're thinking, there's got to be an easier way than this, right? There is. Okay, so let me show you, oops, sorry. Let me show you the alternative, okay? I'm gonna do the alternative in black, okay? Let me just start from a to infinity of the x, the same thing, and then square root of x squared minus a squared, and we'll make the same trig substitution, right? So from 0 to, oh wait, this becomes secant theta, right? Okay, I'm gonna write this much down. See, x was a secant theta, wasn't it? Meaning x over a was a secant theta, right? Now we change this limits of integration right here, right now. Once you substitute 0, what happens? This thing becomes 0, right? You know what I'm saying? Wait, what am I saying? Once you substitute a here. which means secant theta is equal to 1. When is the secant theta equal to 1? 0. You get it? That's kind of what I meant, and I jumped the gun. And then when this thing approaches infinity, meaning vertical asymptote. So where's the location of vertical asymptote of the secant? You kind of have to know your trick in order to be able to do this easier, quicker way. Where's the first vertical asymptote of secant? Secant is 1 over cosine, so we're
Pi over 2.
Pi over 2, cosine becomes 0 at pi over 2, right? This is infinitely nicer now, isn't it? Wait, it's not that. It's still improper integral. Because pi over 2, this becomes a vertical asymptote, so that's still improper integral. You know what I'm saying? However, this side, improper thing disappeared because you can substitute 0 and there's no problem. You know what I'm saying? So it turns out, at least by doing trig stuff, we got rid of one of them. So we don't have to do these two different. You know what I'm saying? Oh, that's half of the work. So most of the times, I'm not sure if I can say all of the times, the convergence side, the improperness disappears on a convergence side. And on a divergent side, we still have, I'm not, okay. Let me say most of the time, okay? Because I'm not sure if it's always true. So we still have to rewrite this. So limit of, somebody give me a letter that we haven't seen.
E.
E. Oh, E kind of, E. Constant E, not our E. E. So we still have to write it like that. You get it? But this is not bad. And then we still have to integrate this, but we'll recycle our work. So this is ln and secant theta plus tangent theta, right? And then from 0 to E. Okay, and then we substitute, so we have limit E approaching pi over 2, E, A, B, C, D, E. Very, very creative, children. So we have secant E plus tangent E, and then minus, and if you put 0, this becomes 1 and this becomes 0, so we have ln 1, which is 0. You get it? Okay, now we take the limit, and once we take the limit, this thing becomes infinity, because as you approach, both of these have vertical asymptotes there. You know what I'm saying? And this is, of course, 0. So we get the same answer, infinity plus 0. Infinity minus 0, technically, which 0 doesn't care. Wow, so this is still half of the work, right? So what have we learned here? When you make a trig sub, instead of bringing x back, you just change these things right there and then. And then many times you get lucky. Okay, this thing still diverged on you, but still it's a half. Get it? Okay, any other questions? Josh?
Oh, I'm just wondering, since we know ln has to be positive there, do we have to put absolute value? Like, I was kind of confused about the absolute value rule. Like, if we know guarantee that's going to be positive
Some
inside,
teachers
can we just
yeah. Some teachers deduct points if it's redundant absolute value. I'm not one of those teachers.
Okay, so to be safe, we can always just put
absolute value all the time. And I don't care. Right, as long as, okay, it's like let's all agree that let's not do this, right? That's just ln2. Right, but if you put ln x, and then x, even if you know x is positive, it's okay. Because technically, this is not an incorrect statement, that's still 2, you know what I'm saying? So it's like, But some teachers actually care about this a lot, and then you have to know when to. And I've heard a rumor that AP sometimes cares. I doubt it. They're mathematicians, right? So it's like, it's one of those annoying things, but it's not annoying enough to take 11% penalty. It's a huge penalty in this 9-point grading scheme. So I don't think I'm gonna, but if you don't simplify fraction, that's offensive enough, right? Don't put dx, like don't put limit. That kind of thing is offensive enough. That's mathematically incorrect, but this is just annoying.
Okay, yeah, thank you.
Any other question? In this problem, as you can see, the numerator is a second degree, denominator is second degree, so this is improper fraction. So first thing we do is divide. So we have x squared plus x plus 1 will divide 5x squared. Okay, now so we have 5 here, so we'll have 5x squared plus 5x plus 5 and subtract, so we have minus 5x minus 5, so we can write minus 5x plus 5 over x squared plus x plus 1. How about that? Good. Then we can break this integral apart. For now, I'm going to write it like this, 5 dx, which is very nice and easy. The next one, I'm going to write 5, common factor out here, and then I'm going to write x, I'm going to leave a little space, there's a reason, you'll see why, x plus 1 over x squared plus x plus 1 dx, for now. You with me? Now we're thinking, okay, the first one is very easy. This one, of course, becomes 5x, right? So that's no problem.
Wait, it should be minus, right?
Huh?
Minus.
Yes, nice catch. This is minus. Okay. How are we going to integrate this? We're stuck at the moment. Now, then, don't you wish there's 2 right there? And why would you want to wish such a thing? Because if there is a 2, then this could be u, and that whole thing is du now, isn't it? Well, oftentimes in mathematics, you can actually write down whatever that you want and adjust it like this. You know what I'm saying? But, that kind of messes this one up. Now this is 2, right? But that also messes with our u sub, because if this is u, and du has to be 2x plus 1, not 2. You know what I'm saying? U. Well, with that, we can still put 1 back in and adjust it like this. How about that? What just happened? Remember, 5 over, if I combine the two, 5 over 2 is a common factor. So here's 1 and here's 1, which is 2, which is same as before. You get it? Who's lost? Now is really good time to let me know. Okay, this one, do you see is ln? And we are sure? And how many of you would like to see this u sub integration? Nah, we are all good? Okay, why am I not using absolute value here? Why is that parenthesis? By the way, if you put absolute value is fine, but why do I put parenthesis instead of absolute value? There must be a reason, because antiderivative of 1 over something, 1 over u is ln absolute value of u. So what happened? Do we know that this is always positive from algebra 2? This thing has imaginary zeros, discriminant, quadratic formula, however you like to think. Wow, okay, too much algebra. Just put absolute value. I'm not going to deduct points for being redundant. And this is our problem. how are we going to integrate that? Right? That one, I'm going to do it down here, okay, and show you separately. So doing that one in blue, so integral of dx over, can we at least complete the square, x plus 1/2 square like that? Then this thing is going to spit out 1/4, and I need 1, so we need 3/4. Too much algebra? Then what kind of trig does it take? You notice I said trig, not trick. Okay, it's gonna look something like this. What do we put in front? Oh, come on, people. The whole motivation is this term right here.
Root 3 over 2.
Root 3 over 2, square root of this whole thingy, you get it? So we need root 3 over 2 in front. That's not enough space. Let's do it like that. Good. Then we need dx, so dx is root 3 over 2, and this is secant squared theta, d theta. And then biggest motivation is this term, 3 over 4. And now if I square this thingy, I have 3 over 4. And here's a 3 over 4 common factor. And then thingy becomes tangent square plus 1, which is secant square, isn't it? So what we need here is now this over this. So this thingy over this thingy. That's why I always write it like that. So these things cancel, right? Say yes. So I will have this thing divided by this. So 2 root 3 over 2, 8. So I will have 2 root 3 over 2, and then d theta. That's it. That will become 2 root 3 over 2 theta. But what is theta? And we get it from here, right? So theta happens to be inverse tangent of, now divide, multiply the reciprocal, right? So we'll have 2x plus, I think we have this, right? 2x plus 1 over root 3 plus c. How about that? Wait a minute, I think I screwed up. This is half, right? This is half, x plus 1/2. See, I have half here. In that case, multiplying 2, so I would have 2x plus 1 like that. So far, so good? Okay, so that whole thing goes up here. And, oh, remember I have 5 over 2? So combine it with this. This is 3. I'm making so many mistakes. This is 3, right? So 5 over 2, so 2's cancel, so we'll have 5 root 3 over 3. And then inverse tangent of 2x plus 1 over root 3 plus c. How about that? Thing, no? Isn't that about the most hideous thing you have ever done, or what? Yeah. Okay, moving down. Questions? Okay, this one looks relatively simple, right? Okay, this one is also trigs up. And this time, what is the trig? Oh, somebody tell me. T is equal to?
5 sine.
5, of course, sine theta, right? So then this thingy, 25 minus t squared will be 25 minus 25 sine squared, so it becomes 5 cosine theta. Good. Do we need absolute values around this? Is the question now. What do you say? You don't. Why is that? Why not? See, what we are saying is theta is equal to inverse sine of t over 5. It's kind of used up. And inverse sine, of course, right, is defined in first and second quadrant. Wait. First and fourth quadrant. And cosine happens to be positive in both of those quadrants, right? So we don't need this. Okay, and we still need dt. So dt is equal to 5 cosine theta d theta. Good? You with me? Okay, so then this thingy becomes, this time we have this times this, right? So we'll have 25. Oh, that's ugly. My hand is so slippery with this thing on, my writing is ugly. It's like pick your poison, right? And then we have cosine square d theta. Now, of course, here we go again. What's the identity here? Cosine square? Somebody tell me, or you want me to figure that out as well?
1 plus cosine 2 theta over 2.
This is 1 plus, so, right, over 2, so over 2 out here, and then this becomes 1 plus cosine 2 theta, like this. Good. Now, then, we integrate. So we'll have theta plus sine 2 theta, chain rule, 1/2 here. Good. Plus c. You with me? Usually we have done these things in indefinite integral, so we substitute, but we have nothing to substitute, so we have to bring t back. Theta here is inverse sine of t over 5, eh? So far so good. Plus, what is sine 2 theta? Okay, let me work that out on the side. 1/2 sine 2 theta. I'm gonna do it here. 1/2 sine 2 theta. What was the identity of sine 2 theta? It was 2 sine theta cosine theta. With that half, it just becomes sine theta and cosine theta. You know what I'm saying? Okay, then what is sine theta? Where do we get it from here? It's t over 5. We could throw the triangle, but it works out. They're all there. Cosine theta, of course, is this. You know what I'm saying? So it is square root of 25 minus t squared over 5. I mean, if you draw the triangle, it turns out to be exactly that. Okay, so that's all of it. So we write, I guess we'll write t over 25. T over 25 square root of 25 minus t squared. How about that? Good? Should we distribute and make this thing look prettier? Yeah. I mean, you don't have to, you can stop right there, but 25 over 2, inverse sine t over 5, and this looks a lot prettier now, plus t over 2, and square root of 25 minus t squared plus c. Oh, infinitely better looking, eh? Okay, how about that? Questions? Okay, then we'll do number 40. Okay, number 40 here. Another trick's up. Now x is positive. I was being nice here, right? X is positive. So what is the trick here? You let x to be secant theta. Then dx here becomes derivative of secant, which is, now if you spit out the answer at this time, the class would be so much better and smooth.
secant theta tangent theta.
Yes, thank you very much. You know what I'm saying? That's like, it's more lively that way. And finally, this thingy, it becomes secant squared minus 1. So this is
Tangent.
tangent theta. Normally, we would put absolute value around it. This one, you have to worry about it because inverse secant is defined in first and second quadrant. Tangent is positive, negative, yeah. But I have that nice condition, so you don't have to worry about it. So things cancel out nicely. You know what I'm saying? So let's see what we have here. 2 d theta. Should we just list it? Yeah, let's just list it. 2 d theta is secant tangent. Then you'll see the magic. And then dx out here, and d theta out there. And then we have x cubed. X cubed is secant cubed. And then that square root thing is tangent. So most of it cancels, right? So we'll have integral of 2 and then cosine squared, 1 over secant squared. Now we have done this one before, right? This cosine squared just in previous problem was 1 plus cosine 2 theta over 2. We'll cancel this too. And this problem was designed to be very nice. So we have 1 plus cosine 2 theta. D theta. You get it? Say yes. Okay, now integrate. So we have theta plus sine 2 theta. This is almost recap of the problem we just did. And then, of course, sine theta, right? Okay, I'll do it on a side again. 1/2 sine 2 theta is equal to sine theta cosine theta. And then look at what sine theta is. Now we have to draw the triangle and worry about these things a little bit, right? Because we have a different conditions. So I'm gonna draw it here. And this is first quadrant only. So let's draw it like that.
How do you know what quadrant it is?
Oh, usually it is first and second, but this condition is positive only. You get it? Because x is positive only, meaning secant theta is positive only.
Worse, right? Like caught me. Who knows what he would have done? Thank God Alexis won.
What was that? Okay, first quadrant, right? This is positive, so. Okay, so I'm gonna throw that triangle like that. I normally say you don't put anything on the variable on the hypotenuse because we could go to second quadrant, but in this case, it is first quadrant only, so we can put x here and 1 here, and this could be theta. You know what I'm saying? That way, secant theta is equal to x. You know what I'm saying? And then this side, of course, is x squared minus 1, which looks familiar in this problem. So I need sine theta, which is this thingy over this thingy, so that's square root x squared minus 1. And cosine theta, of course, is this thingy over that thingy. You know what I'm saying? So we need 1 over x. You get it? You get it? Okay. Come back here. So let's list the answers. So theta, of course, up here is inverse sine, inverse secant of x. So we'll put inverse secant of x and then plus all of that, right? I'm going to put 1 over x first, then square root of 25. Wait, whoa, 25 is from previous problem. X squared minus 1 plus c. How about that? Good. Y'all with me? Questions? Your facial expression tells me that you're not with me. You kind of get it, but you don't at the same time. I think that's the last problem. Any question before I stop the recording?
Miss Kim.
Uh-huh.
Why is sine theta square root of x squared minus 1 only? Shouldn't that be...
Oh my God, I missed it, right? Yeah. Very nice catch, very nice catch. It's over. Hold on. I'm gonna make this thing look a lot prettier. Oh my God, it's over x, right? Yeah, we need all of that. So over here, let's see if I can squeeze that square in. Square, how about that? Nice catch. Okay. Any other questions?